Good afternoon, everyone. I'm Sravanthi from Department of Aeronautical Engineering. So today we will be doing a numerical on engine sizing in our second module of flight vehicle design. So I've taken a numerical from Raymer textbook, right? So in the last class we have seen about the refined sizing, right? In the first module, all we have done was a conceptual sketch and how to estimate the takeoff weight of a particular aircraft, right? So in the second module, we were studying about the how to do a actual sizing or how to do a refined sizing, and it has got two types. One is a fixed engine sizing, then the other is the rubber engine sizing, right? And we have seen what are all the different things that need to be added in the rubber engine sizing. Uh, all of them are going to be same. We need to find out the weight estimation, or we need to calculate the fraction. All the segments need to be calculated. Then we need to calculate the weight estimation, empty weight, fuel weight. Then we do some iterations by guessing the weight and by coming up to a calculated weight, right? Except that we are going to include here the weight drop, right? If there is any payload drop or if there is any weight drop, those parameters are also included, and we are refining the complete sizing of the particular given aircraft, right? So the last class we have seen all the formulas or how to do certain estimations, all the different parameters we have studied. So today we will be seeing a problem on how to refine that particular size, right, by considering a payload drop to it, a weight drop or a payload drop to it, right? So DR3, a lightweight super cruise fighter. So this has been taken from the Raymer textbook, right? You can see that. So a lightweight super cruise fighter is been taken, and it has got the this particular mission profile has also been given, right? So mission profile stating 0 to 1 takeoff, 1 to 2 climb, 2 to 3 cruise, then 3 to 4 we have an acceleration, right? Then we have a dash segment, 4 to 5, then 5 to 6 there is a combat, right? Then 6 to 7 you have a weapon drop or a weapon release, we say. And 7 to 8 there is an acceleration again, then dash, then again cruise segment, then it follows, right? Whatever the segment mission profile we have seen, the same mission profile is going to be followed here. Dash segment, cruise segment, descent, loiter, descent, and land, right? So air to air, right? So for this particular mission profile design, we need to do the sizing, right? A refined sizing, right? And also the values are mentioned here. The value stating 3 and 10. 3 and 10 why? Because here my 3 is also cruise, my 10 is also stating cruise, right? So for both the cruise, its range is same, right? It's going to be 200 nautical miles. NM is saying nautical miles. Then 5 and 9 are dash segments. So for dash segments, it is 50, right? Then 6 is going to be compact. Only 6 is going to be a compact here, right? So 6 is going to be for 3 minutes, right? At a maximum thrust at Mach of 0.9 at 20,000 feet. Then 12 is going to be the loiter. Loiter segment we have one loiter, right? So loiter segment is again 20 minutes at sea level, at best loiter speed. Then 7 is going to be a weapon release, right? So here 7 is stating a weapon drop. So that weapon drop is for 400 pounds missile only, right? So the payload that has been carried out here is a two advanced missiles, right? Two advanced missiles, 200 pounds, right? Then the advanced gun is also there, 400 pounds, and 750 rounds armor, 490 pounds. Then the pilot weighing 220 pounds. It all is the weight of the payload. Okay. So now with this, we will go and do a sizing of it. Okay, a refined sizing when we have a weapon drop in it, right? And yeah, some other parameters are mentioned here. Takeoff and landing, 1000 ground roll, approach speed less than 130. Maximum Mach is greater than 1.8, accelerating from 0.9 to 1.4 at 35,000 feet, right? So a few data which is going to be related or what we want in our calculation, right? So first, what is that I am going to do here? All we want is to find the calculated weight, right? In order to find the calculated weight, we want to make iterations, right? By guessing the weight, right? With that weight, what you have guessed, you are going to find out the weight fraction. You are going to write the fuel fraction. Then you have a calculated W naught here, right? So this is what we want at the end, right? In order for me to come to this particular iterations, we need to find WF, we need to find WE by W naught, right? Or we want rather WX by W naught, which is all the segments, right? We have 14 segments here, so I expect all, so 14 meters, right? So first of all, we will be calculating the W14 by W naught, or which is WX by W naught, then empty weight fractions, then fuel weight fractions. Then we do the iterations, right? So again, in all of these things we have, and all of these things are going to be followed at each segment, right? So first of all, we will be doing the empty weight fraction here. Now, for an empty weight fraction, as the aircraft or the particular profile, it is saying D3, DR3 lightweight supercruise fighter air to air. So it is going to be a jet, right? Now for a jet fighter aircraft, we know WE by W naught, right? So I have this formula, right? WE by W naught is my formula, right? Taken from the Raymer again. Now for this particular formula, all the constants or all the values that we are going to incorporate it for a different type of an aircraft, right? Now here it is my fighter. So I will take all the values of the fighter, right? My A, B, C1, C2, C3, C4, C5. I take all of them and I try to substitute here and I get a value of it, right? So finally, when you go and substitute all of the fighter particular constant values, then we obtain my W by W naught is going to be 1.75 into W naught is a unknown term, right? So W naught power of minus 0.1 minus 0.018. So this is the empty weight fraction, right? Calculated from the previous trends estimation. Then it is going to be a mission segment weight fraction. So I have 14 segments, right? So I'm going to calculate all of them. Right. So this is what is my mission segment weight fraction. This is what we are going to calculate for all of the different segments that has been shown. Takeoff, climb, cruise, then there's an acceleration, then there is a weapon release, then we have a cruise again, then there's a descent, there is a loiter, then right, land. So for all of them, we're going to calculate of all of it, and we know that a takeoff weight initially, right? So initial W1 by W naught is 0.98. We know this; it is going to be a fixed value. Now, when you're climbing, when I'm trying to climb, right? So this is my climb segment. Now, during climb, we have said that in our first module, when we are talking about the mission segment weight fractions, we had a fixed value for climb, right? So we had a fixed value for takeoff, for climb, and for land. But here, we have a fixed value for takeoff, but we don't have a fixed value for climb. We are going to calculate it in terms of a Mach, right? So this is what we have said in the last class, and it is different for a subsonic and it is different for a supersonic, right? So if we are talking about a subsonic, then it is going to be W2 by W1, as it is going to be a second 2 to 1, right? So W2 by W1 is going to be 1.0065 minus 0.0325 of Mach, right? So Mach again in the question is said it is 0.9 at 35,000 feet. So we are going to consider Mach to be 0.9. So my answer at the climb segment is going to be 0.977. Right? So this is what I get for a climb of a Mach considering to be a 0.9. Then again we need to consider the cruise, right? Next is my cruise. Right now for cruise 3 to 2. Now what we know for a 3 to 2 of cruise, how do I find out for a cruise and loiter? We have equations from Bergurite, right? from Bergeret range equations, we said that W3 by W2 is equal to exponential of minus R into C by V into L by D, right? This is what we have said, right? Same goes with the loiter also, right? So now, for this particular to calculate, I want to know what is range, right? Range is already given the question. Then what is C? C is my specific fuel consumption. Then V is the velocity. Then L by D. L by D, we have separate calculations. We have taken it from the charts and we have calculated it, right? Now here I have a different way of approaching it, right? So my L by D is different here. Now my L by D here is going to be 1 by QCD naught by wing loading plus wing loading to power of into 1 by Q pi AE aspect ratio. Q is the dynamic pressure, W by S is the wing loading, right? Now for that, my Mach is still zero point 0.9 at 35,000 feet, velocity is 876 feet per second, and dynamic pressure is 283 pound per feet, right? Now, these are all the data we know, and we are going to calculate this particular L by D. Dynamic pressure, you know, CD naught is known. CD naught for a fighter is 0.014. This should be a known term. Then W by S is going to be taken, right? So W by S is going to be 54 here, wing loading is 54. Then 1 by dynamic pressure, you have a value, aspect ratio it's 3.5, right? E is going to be 0.86, right? So from there we are going to get L by D and substitute here. V you know, R we know, specific fuel consumption we know, and we get a W3 by W2 segment here. Okay, now next is going to be something like this, right? So I need to calculate this particular condition here. In order for me to calculate, first of all, now we have done here W by S for this complete 54 for entire aircraft. Now I want a wing loading for a particular segment, right? Now we are in the cruise segment. So at a cruise segment, I want my W by S, right? In order for to calculate the W by S, we are going to do it, right? So W by S is going to be W naught by WS into 1 by 0. Let me write in this way: 0, 1, 2, 3, right? W naught by WS is going to be the first wing loading for an entire aircraft. We know that, right? Then, then 1 to 0, 2 to 1, right? So up to this point, right? Up to this point, W1 by W naught we know at during takeoff. What is the segment weight fraction? We know 0.98. Then W2 by W1 is also known. We have calculated it 0.977 for a climb, right? So with that, we come to a point of W by S during cruise is going to be 54, right? So if we understand this, this is what we are going to take it in the next steps for the next fractions, right? Now, for a particular of max 0.9 at 35,000 feet, specific fuel consumption of 1.07, we are going to calculate our W3 by W2, which is exponential of minus R into C by, let me just write down here, exponential of minus R into C by V into L by D, right? Range is 200 nautical miles. Nautical miles need to be converted. Then specific fuel consumption is 0.94. 0.94, that is like after reduction, right? So we are trying to reduce for 10% and 20% again. So you're coming down, then converting it per hour to seconds. Then speed, you know, right? Speed we are flying at 876 feet per second. Okay, into L by D. L by D you have attained here. We have calculated L by D and we got an answer for L by D. Then that is how we go and calculate our W3 by W2, a cruise segment fraction to be 0.967. Okay. Then next is your acceleration, right? So next is the acceleration segment. Acceleration segment is W4 by W3, right? So now I am trying to, I have cruised it, right? We have taken off, we have climbed, you have cruised. Then once after your cruise, you're trying to accelerate the vehicle. You're trying to accelerate the vehicle means you're trying to consume the fuel and you're trying to reduce the weight here, right? Now here, I'm going from subsonic to supersonic region, right? So acceleration going for supersonic, then your Mach is going not to be only 0.9, it is going to be in a region of 0.9 to 1.4, right? So therefore again, now again I go and calculate W4 by W3 in terms of that 1.4, in terms of 0.9 to 1.4, right? Now I have a particular formulas with respect to supersonic speed. We have seen here in terms of climb, we have a formula, right? This is the formula. I'm going to take it and calculate it here, right? So at 1.4, because we are going to be, acceleration is going to be supersonic, so we take supersonic formula and we calculate that value. And then W4 by W3 at 0.9 to 1.4 is nothing but this particular value, 0. From here what you attain by the previous segment fraction, which is 0.977. Okay, you get that. And from there we go and calculate this. This is what we are going to get. It is 0.984. Okay, so that is going to be the acceleration. Then next we had a dash segment over there, right? So the next segment is dash segment, which is W5 to W4. Now in a dash segment, the range is given as 50 nautical miles. Again, as it was flying at a supersonic regime, so 1.4 at 35,000. Then the speed has changed. Again, the dynamic pressures are going to be changed. So with respect to that, my W by S is also going to change, right? So in the previous segment, we have considered till W2 by W1, right? So because we are talking about the cruise, so we have taken till that point. Now next is your till your dash segment. So we consider till that point and we take all the weight fractions with respect to your wing loading of the aircraft completely. So it is 56 of complete aircraft. Then the first segment fraction was 0.98, second was 0.977, third was 967, and the fourth is 984, right? What you have attained in the acceleration. So all of them should give you 51, right? So here my W by S is going to be 51. And CD naught at a supersonic 1.4 is going to be 2 times of CD naught of 2 times of subsonic. So here it is going to be 0.028 because there is also 0.014, right? So then K value also we need to calculate it. Then we finally get that L by D. L by D also calculated with respect to the formula. Then finally it is going to be W5 by W4, right? So we can calculate from here W5 by W4 from L by D, right? So specific fuel consumption after all reductions, it was 1.06 previously. It is, I think it is 1.07. Yeah, 1.07. So now reduction 20%. So we come down to 1.06. Then we calculate the Bergerite equation for 5 to 4 segment. It is going to be 0.975. Right. Then the next segment is combat. Right. So for combat we have set different formula, right? So combat D is going to be 3 minutes, right? Then thrust to weight ratio is 0.588. Then the formula is Wi by I minus 1 equal to 1 minus of specific fuel consumption into thrust to weight ratio into D, right? So here my segment fraction is 6 to 5. So W6 by W5 is equal to 1 minus of specific fuel consumption. Specific fuel consumption after reduction, it is going to be after reduction it is going to be 1.57 per hour. Per hour need to be converted, right? Then thrust to weight ratio. Thrust to weight ratio is 0.588. Then D is given as 3 minutes. Minutes again have to be converted. Then we finally attain the combat segment fraction, which is 0.94, right? Now this weight drop we are not going to consider. We have not considered it during our first model problems, right? So there no weapon drop or no weapon release. So here when you are trying to refine the sizing or when you are talking about the rubber engine sizing, only then we are going to consider this particular parameter or this particular segment too. The next is again acceleration again. Acceleration again is similar. This acceleration dash and cruise segments are going to be similar to the previous one because we'll just see the mission profile. So we know takeoff value. Climb we have calculated by considering the Mach number formula. Cruise we have done by considering the Bergert range equations, right? By calculating the L by D's and W by S. Then acceleration we have found out same. Dash segment also we have done. For a combat we had a different formula with respect to D and T by W that we have calculated it. So these are all the things we have calculated to one side. Then if we see the other side, now other side is again the same of it because the values are also almost same. So acceleration, this acceleration is going to be equal to this dash segment is going to be equal to this particular dash segment, and the cruise segment is again is going to be equal to this particular cruise segment, right? So 10 to 9 is equal to 4 to 2. 9 to 8 is equal to what is 9 to 8? Acceleration, right? So that acceleration is equal to 5 to 4. Yeah, right? So that part of the segments are equal to this part of it. So acceleration is same, dash is same, the values are same. Okay. Then cruise is also again same, right? So far we have done segment fraction till W10 by W9, right? So next is a loiter segment. Now loiter again we know. Loiter segment again we're going to take it from the Bergerate endurance equation, right? So from Bergerate endurance equation we need again this L by D. We calculate dynamic pressure. We calculate wing loading, right? So endurance is going to be 20 minutes. You are loitering for 20 minutes. So 20 minutes converted to seconds. Then W by S, whatever the segments we have finished, right? So whatever we have approached here till this particular point, I feel, right? So all the segments weight fractions need to be considered here, correct? So first of all, the wing loading of the entire aircraft, then 0 to 1, 1 to 2, 2 to 3, then there is an acceleration, right? So we consider all of them. All of them mean W naught by Ws of entire aircraft. 1 to 0 we had a takeoff. Then 2 to 1 was climb. 3 to 2 was cruise. Then 4 to 3 was acceleration. Then there was a dash segment. Then there is a weapon drop. Then again all repeated acceleration, dash and cruise. Right. So all of them considering till that particular point, we are going to write all the values till there and get a wing loading at that segment. At a loiter segment is going to be 44, right? Now for that again my dynamic pressure, speed, and with respect to that we calculate L by D. Then when you know L by D, again specific fuel consumption, because it is going to loiter and descent, again you are coming down to this particular regime, and then we go and calculate endurance equation. Okay. So my endurance equation is going to be minus V into C by L by D, right? Minus C by V into L by D. Okay. So that is going to be loiter, then descent, right? So descent for landing are again given known factors, known values. So the 13 by 12 is a descent. It is going to be 0.993. Then the landing segment is going to be 14 to 13, which is 0.995, right? So now we have completed all 14 segment fractions calculations of it. Then finally, if you multiply all of them, it is going to give the total mission weight fraction. Multiplication of all the segments, it is going to be 0.7586, right? So that is the first step. Then we have calculated or we have written what is WE by W naught. It was in terms of W naught, right? So then we have calculated all the mission segment fractions. All the mission segment fraction, all the multiplications of it, right? By considering a different each segment, we got this particular value. The next is the fuel fraction, right? So fuel fraction is going to be 1.06 into 1 minus of Wx by W naught, right? 1.06 is the tolerance. Now with respect to that, we got a value for a fuel fraction. Now we need to go and iterate it, right? Take the table, do the iterations of it, then finally we estimate what is calculated W naught, right? In order to do that, or before doing that, what we do is we are trying to adjust the empty weight fraction, right? So for sizing, we are going to need to adjust the empty weight fraction by assuming, or you are just adding 200 pounds extra here, right, in a weight fraction, empty weight fraction. So my empty weight fraction was 1.75 into W naught power minus 0.1 minus 0.018. In order to just adjust things in the empty weight, we are adding 200 pounds here. Now we are going to size it or iterate it, right? When you're trying to iterate it, the numerator is what? My W naught is what? Crew plus payload by 1 minus of empty weight fraction minus of fuel weight fraction. This is your W naught, right? So I have fuel weight fraction, I have empty weight fraction in hand, right? So crew and payload, right? So in order for me to write crew and payload, my crew and payload is going to be crew is 220. So here we have considered the C plus payload, W crew plus payload weight. So crew weight, pilot weight is 220 here. Then the other weight, which is payload weight. So we are carrying all of these things. So we go and calculate 2 into 2 advanced missiles, and we have advanced guns and rounds armor, right? So all of things are going to be in this particular crew and payload weight. So we calculate, so that is going to be 1460 pounds. Now with respect to that, we make iterations now, right? We make iterations and we try to guess. We are guessing at 20,000, right? When you guess at 20,000, when you go and substitute here, you're going to get an empty weight fraction, right? So empty weight fraction, I have attained a new empty weight because W0 was unknown term here, right? You substitute your guess weight here, right? When you're going to substitute a guess weight, you get a new empty weight fraction value, and with respect to that, we get a W calculated one here, right? Because we know WC plus WP by 1 minus of WE by W0, WF by W0, right? So we get a new calculated weight. Again, we repeat this iteration until there is a convergence, right? Until you are going to an approximate value, and that is how you finally calculate the weight of it, right? By considering a weapon drop or release, right? So this is your refined sizing or English. Okay. So this is how we are supposed to do a numerical when it is asked for a rubber engine sizing or a refined sizing, right? So all I want is to calculate the W0 here, calculate a W0, the correct one. In order for me to find the correct weight, I have to do iterations. I have to guess by having the empty weight and fuel fraction and missing segment fraction. So in order for me to do that, I first of all go and calculate all the segment fractions, right? Just summarize things here, right? So I'm going to calculate all machine segment fractions. At each segment, I need to calculate all of them with respect to its wing loading or Mach number or its dynamic pressure and speed. You try to calculate all of it. You multiply all of it, it will give you the machine segment fraction. Then you go and calculate the fuel weight fraction. Then you write empty weight fraction with respect to the previous trends that has been given, right? If it is a fighter aircraft, we take all of those things and we calculate empty weight fraction. Empty weight fraction is going to be having a unknown term of W0, right? Once you're finally done with it, start iteration, start to guess a value and get or stop when you get a approximated calculated weight to it, and that is going to be your actual takeoff weight, right? So this is a refined sizing, and today we are going to stop at this point, and tomorrow we will continue with the fixed engine sizing. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.